In this video, I'm gonna explain how to solve the equation from the GHR model to derive the flow density relationship from the Greenfield model. So first, I'm gonna briefly explain the GHR and Greenfield model. So as I have explained in the other video, GHR model assumes that follower's response is proportional to speed of the follower, relative speed, and space headway. And follower's response is written as acceleration in the equation. And in the Greenfield model, it assumes that in the uninterrupted traffic, speed and density are linearly related. So this graph here shows the relationship between speed and density. As the speed goes up, density of the traffic goes down, and as the density goes up, speed of the traffic goes down. So this right here equation shows their relationship. So V equals A times K, which is speed equals A constant times K density. So K here can be calculated by 1 divided by space headway. So now I'm gonna solve the problem. First, this is the equation from the GHR model. This xn plus 1 is the follower's position, and xn is the leader's position. And 2 dot here means second derivative, and second derivative of the position is acceleration or follower's reaction. So the follower's reaction is equal to B, which is a sensitivity parameter, times I derivative, which is, so I is a space headway between leader and the following vehicle, but because right here is derivative of I, it's relative speed respect to the time t. And right here, this is an equation for the sensitivity parameter. Right here, A, M, Q are constants, and top here is a derivative of the follower's position or the speed, and bottom here is the space headway. So what this means is that sensitivity is directly related to the speed of the follower and has an inverse relationship with the space headway. And the space headway can also be written as leader's position xn minus follower's position xn plus 1. So now I'm gonna start solving the question. I'm first gonna substitute this B into this equation here. So it can be first written as acceleration of the follower equal A times speed of the follower divided by the space headway Q times the relative speed, which is T. And the problem gives us the value for the constant m equals 0 and q equals 2. I'm gonna plug it back here. So the acceleration of the follower equals A speed of the follower T2 times the relative speed. So if you rewrite this, it becomes, so the top here, oh, I didn't write it. this is 0. So because this right here is 0, it becomes 1. A times 1 over this 1 T2 times the relative speed here. So, like I explained earlier, the space headway can be also written as leader's position minus follower's position. So I'm gonna plug that back in also. So it'll be A times xn minus xn plus 1, 2 times xn minus xn plus 1 relative speed and the acceleration of the follower. So now I'm gonna take the integral on both sides. So integral of the acceleration now becomes the speed of the follower, which can be written with 2 dots. So, and also I'm gonna take out A because it's right here because it's constant. So A integral 1 over space headway, plus H minus times the relative speed. So now to solve this problem, I'm gonna use the substitution method here. So I can let u equal xn minus xn plus 1. And if you take the derivative of u, it becomes du equals the relative speed respect to the dt. So what I can do is I can let u substitute right here, and then du can substitute relative speed here. So this follower's speed equal a 1 over, it is 1 over u square and du. And if the integral of the 1 over u square is u negative 2 plus 1 divided by negative 2 plus 1, which is equal to negative 1 over u. So if you solve that here, it is a times negative 1 over u. So now I'm gonna plug this back into u here. So the speed of the follower equals negative a times 1 over xn minus xn plus 1, which is a space headway here. So 1 over space headway, like I explained earlier, this is equal to density from Greenschot model, which is k equal 1 over space headway. So I can now substitute k into this position. So k equal 1 over space headway, or 1 over xn minus xn plus 1. And I forgot to put c here. Plug in c. So speed of the follower equals negative a times k plus c. So this right here shows that the speed of the follower equals the constant a, negative a, times the k density plus the constant. And if you look back, this shows the Greenschot flow density relationship. It is same thing as here, which is v equal a times k, speed equal constant times the k density. And that's how you derive Greenfield model from the GHR car following model. And